These three are intervals, and those two are points. All right. Any question about that one? You guys are okay with the polynomial? Let's try a trickier one. You afraid?
Yeah. It's the fully compare.
48, the next one. Rational function. Same question. Determine concavity and inflection points. 48. It is f of x equals 1 over 1 plus x squared. That looks familiar. What is 1 over 1 plus x squared? It's the derivative of tan inverse. Isn't it? Isn't that derivative of tan inverse?
Yeah.
All right. All right, who cares? Whatever. All right.
I was like, hold on.
Okay, got to run through the list, right?
Yeah.
So f prime, I want to get the first derivative, so we get the second derivative, so we can check on concavity. First derivative, we'll play, we'll just do this. Write this as 1 plus x squared to the negative first. It's better than a quotient rule. Quotient rule is silly when you have a constant above, right? So you pull down the negative 1, so you get negative 1 plus x squared to the negative 2, times the derivative of the inner function, which is 2x. So if we clean it up a little bit, it will look like a negative 2x over 1 plus x squared squared. Same thing we would have gotten from a longer quotient rule. Okay? Make sense so far? Fine. Double prime. Second derivative, so we can check on concavity. Now, what we're going to do in the next section, tomorrow, is going to be, you're going to apply both the first derivative test and the concavity test to help you graph the function. So we would have actually done something with the first derivative at this stage if we were graphing. We would have found the max and min values. Okay? But all the question asks us about is concavity, so we go straight to the second derivative. So we might as well use the quotient rule here. So we'll have the bottom times derivative of the top, which is negative 2, minus the top times derivative of the bottom. Derivative of the bottom is, bring down the 2, 1 plus x squared to the first, times the derivative of the inside, which is 2x. Agreed? Over bottom squared. So that makes it the fourth. Does that look right?
Yeah.
For a quotient rule? Alright, now we gotta clean this stupid thing up. First thing you can do is what? Cancel a 1 plus. Right. Cancel 1 plus x squared from every single term. There's a 1 plus x squared here, there's 1 plus x, there's 2 there, and there's 4 there. So take 1 from each.
Well, what about that negative 2x? Or it's because that's...
This is all one term, because it's all multiplication.
Oh, okay.
So I can remove this factor if I want. I'm going to remove that factor, remove one of these and one of these. So it'll be a 1 plus x squared to the first times negative 2, with negative 2 in front. If I take this one away, all I have left is plus 8x squared.
And what 1 plus x did you cancel out?
Say again?
What 1 plus x did you cancel out?
I'm going to take away this one,
Okay.
one of these,
Okay.
and one of these. One from each term.
Okay.
From each term. So the bottom is now a cube instead of a 4th power. Equals. The top simplifies. Negative 2 minus 2x squared. Negative 2x squared plus 8x squared, 6x squared. So we have 6x squared minus 2, and below, still the 1 plus x squared to the cube. All right. So there's our simplified second derivative. You can factor out a 2 from the top, but so when is 6x squared minus 2 equals 0? When x is what?
Square root of 1/3. Square root of 1.
Square root of 1 over 3, right?
Yeah.
Okay, so 1 over root 3. So square root of 3 on 3. Is that right? This would lead us to x squared equals 2 on 6, which equals the third. Take the square root of both sides, get x equals plus or minus what Lou was saying. And then if you rationalize the denominator, that will give you plus or minus root 3 on 3. So there's two what? We don't call them critical values now, because they're not coming from the first derivative, they're coming from the second derivative. So we're going to call them possible inflection points. We don't know that they are yet. So they're going to be possible inflection points. Just like critical values are possible maxes and mins, we just have a better term for it. We call them critical values. So it's a possible thing. About down here, what x is going to make this equal 0? What do you say, Lou? No x. X squared plus 1 is always positive, so it's never going to be 0. Oh, this is a red herring. So we have 2 possible inflection points.
Wait, why did we cancel that out?
Because it can't happen. If you take a square and add 1 to it, there's no way it will ever be 0, right? With real numbers. Number line. Let me ask you a quick question. I don't think they wrote in the problem. What's the domain of this function?
I don't know.
What do you say? Don't know? That's not
Can
good
we
news.
just take it from the bottom part of the original one?
They did not tell us the domain. What's the domain of 1 over 1 plus x squared?
Isn't this the main?
Isn't it all?
Oh, really? 71. Oh, wait.
It's all reals. All reals.
Got the x
The bottom will never be 0. That's exactly what we just established here. The bottom, which was this inner part here, will never be 0. So I'm not worried about anything. This thing's good to go. All reals.
So
Another thing you should note about this function is it ever going to be 0? Does this function have any x-intercepts? Is it ever going to be 0?
Nope.
Nope. Because that would require the top to be 0. The top is fixed at 1 for all time, right? Can it be negative? No. I've got a positive over, this is always positive, this is what we just established here. This is always positive, therefore never 0. So this function is always positive, it has no x-intercepts, and its domain is all reals. Okay? So now, what is its concavity? So we have plus and minus root 3 on 3. So we construct our interval, which is the whole real line. That's what we're trying to establish here. What is the, what's our little test case going to look like here? So we've got negative root 3 on 3, and we've got root 3 on 3.